Hi, welcome back to our course. In the previous course, I believe you have learned about Hadoop and have used Hadoop. As you know, the emergence of Hadoop has solved the storage and calculation problems of massive data in the early 21st century and has been widely used in the world. Nowadays, many enterprises build their Hadoop clusters on traditional servers or cloud servers for storage and analysis of big data. In this course, we will introduce you to E-MapReduce, a large data analysis product from Alibaba, where you can use Hadoop to process data. After mastering its basic usage, you will also learn how to use the Hadoop ecosystem component Hive in EMR, which is a very useful data analysis tool. Let's first look at today's learning goals. Upon completion of this course, you will be able to know what E-MapReduce is, know the advantages and the usage scenarios of E-MapReduce, master the purchase and use of E-MapReduce, understand how to use Hadoop on E-MapReduce, know Hive's principles, understand how to use Hive on E-MapReduce. Let's move on to today's course. First, what is E-MapReduce? In general, to use distributed processing systems, such as Hadoop and Spark, the following actions are recommended. Steps 8 to 10 relate to the application logic of users. Step 1 to 7 are early preparations and tend to be difficult and cumbersome. As you may already know, if you use a cloud server such as ECS, you don't need to perform steps 1 to 5 again. Yes, that's the advantages ECS has over traditional servers in building Hadoop clusters. But Alibaba is also considering providing you with customized instance services on the basis of providing cloud servers. E-MapReduce is a customized ECS image for your big data business. It can keep you from going through steps 6 to 7. After purchase, you can no longer go through any software installation because they are running well and waiting for you to use them. This is more user-friendly. I believe you have a preliminary understanding of E-MapReduce. Next, take a look at the official introduction. Alibaba Cloud Elastic MapReduce, EMR, is a big data processing solution that runs on the Alibaba Cloud platform. EMR is built on Alibaba Cloud ECS instances and is based on open-source Apache Hadoop and Apache Spark. EMR allows you to use the Hadoop and Spark ecosystem components, such as Apache Hive, Apache Kafka, Flink, Druid, and TensorFlow, to analyze and process data. You can use EMR to process data stored on different Alibaba Cloud data storage services, such as Object Storage Service, OSS, Log Service, SLS, and Relational Database Service, RDS. E-MapReduce provides an integrated solution of cluster management tools, such as host selection, environment deployment, cluster building, cluster configuration, cluster running, job configuration, job running, cluster management, and performance monitoring. With E-MapReduce, processes such as procurement, preparation, operation, and maintenance are managed, allowing you to focus on the processing logics of your applications. E-MapReduce also provides flexible combination modes, allowing you to select different cluster services according to your needs. For example, if you want to implement daily statistics and simple batch operations, you can choose to run only Hadoop services in E-MapReduce. If you still want to implement stream-oriented and real-time computing, you can add Spark on the basis of the Hadoop service. The core component directly oriented to an E-MapReduce user is the cluster. An E-MapReduce cluster is a Spark and a Hadoop cluster consisting of multiple ECS Alibaba Cloud instances. For example, in Hadoop, generally some daemon processes running on each ECS instance make up a Hadoop cluster. The nodes running name node and the resource manager are known as master nodes, while those running data node and node manager are called slave nodes. For example, the following figure shows an E-MapReduce cluster consisting of one master node and 3 slave nodes. Among them, the master node has 2 IP addresses as access entrance, while the slave node has only private IP address. E-MapReduce has some practical strength over self-built clusters. For example, it provides some convenient and controllable means to manage its clusters. In addition, it also has the following strengths. Easy to use. You can quickly create clusters without the need to configure hardware and software. All maintenance operations are completed on its web interface. Cost effectiveness. You can create clusters and dynamically scale in and out the number of compute nodes based on current computing needs. Stability. EMR provides a deeply optimized cluster environment, automated background maintenance, and multiple online support channels. Security. EMR supports Kerberos, authentication, and data encryption. You can use RAM users to refine the management of service permissions. In this section, you will learn how clusters, jobs, and execution plans are used in E-MapReduce. You will also learn how to create a MapReduce Pi job, run it successfully in the cluster, and check the results. At EMR console, click Create Cluster. You need to authorize a default EMR role to use the service. Click on the link to confirm the authorization. The first page is software configurations. Use the latest EMR product version. Use default software configurations including Hadoop components, Hive, and Spark. The second page is hardware configurations. Select Pay as you go. If there is no security group, enter a name to create new security group. The third page is basic configurations. Enter the name of the cluster. Enter the password. Click Next. Click Create to create a cluster. Wait about 10 minutes. After the creation is complete, the user can see that the status of the cluster is displayed as idle. Click Cluster Name. You can see Cluster Overview here. Next, start creating our job. At the top of the page, click the Data Platform tab. Select a project. Click Edit Jobs. Click New Job. Paste the Hadoop script. Click New Workflow. Design a workflow that starts and ends nodes. Choose the MR job we designed. Click OK. Click Run. View job logs and confirm the results. My result is about 3.24. In this section, let's talk about Hive. Hive is a data warehousing infrastructure based on Apache Hadoop. Hadoop provides massive scale-out and fault-tolerant capabilities for data storage and processing on commodity hardwares. Hadoop is a popular open-source MapReduce implementation, which is being used in companies like Yahoo, Facebook, etc., to store and process extremely large data sets on commodity hardware. However, The MapReduce programming model is very low level and requires developers to write customer programs which are hard to maintain and reuse. Hive provides standard SQL functionality, including many features for analytics like OLAP functions, subqueries, common table expressions, and more. After the user enters the SQL, Hive automatically uses the computing framework of the response to realize the function, which eliminates the time for the user to write the program by himself. This means that users only need to use SQL to analyze large data, which is very convenient. This is also an important reason why Hive is popular. Hive is designed to enable easy data summarization, ad hoc querying, and analysis of large volumes of data. It provides SQL, which enables users to do ad hoc querying, summarization, and data analysis easily. At the same time, Hive's SQL gives users multiple places to integrate their own functionality to do customer analysis, such as user-defined functions, UDFs. Hive is not designed for online transaction processing. It is best to use for traditional data warehousing tasks. By the way, here's a brief introduction to SQL. Structured Query Language. SQL is a domain-specific language used in programming and designed for managing data held in a relational database management system, RDBMS, or for stream processing in a relational data stream management system, RDSMS. SQL has great flexibility and powerful functions, but also very simple, making it very popular in the field of data analysis. There are subtle differences between the support of different databases or software for the SQL language and the standard, and Hive is no exception. Hive supports queries expressed in an SQL-like declarative language, HiveQL. Later in this course, we will learn some about HiveQL. The following components are the main building blocks in Hive. Driver, the component that manages the life cycle of a HiveQL statement as it moves through Hive. The driver also maintains a session handle and any session statistics. Query compiler, the component that compiles HiveQL into a directed acyclic graph of MapReduce tasks. Metastore, the component that stores the system catalog and metadata about tables, columns, partitions, etc. Execution engine, the component that executes the tasks produced by the compiler in proper dependency order. The execution engine interacts with the underlying Hadoop instance. Client components like the command line interface (CLI) and web UI and the JDBC ODBC driver. When you store data in Hive, Hive generates a Hive directory on HDFS to store Hive files. Metadata can match file data according to these directory names. The Apache Hive Data Warehouse software facilitates reading, writing, and managing large datasets residing in distributed storage using SQL. Built on top of Apache Hadoop, it provides tools to enable easy access to data via SQL, thus enabling data warehousing tasks such as extract, transform, load, reporting, and data analysis. A mechanism to impose structure on a variety of data formats. Access to files stored either directly in Apache HDFS or in other data storage systems, such as Apache HBase. Query execution using Apache Hadoop MapReduce, Apache TZ, or Apache Spark frameworks. Hive provides standard SQL functionality, including many of the later SQL 2003, SQL 2011, and SQL 2016 features for analytics. Hive's SQL can also be extended with user code via user-defined functions, UDFs, user-defined aggregates, UDAFS, and user-defined table functions, UDTFS. There is not a single Hive format in which data must be stored. Hive comes with built-in connectors for comma and tab-separated values, CSV, TSV text files, Apache Parquet, Apache ORC, and other formats. Hive is not designed for online transaction processing (OLTP) workloads. It is best used for traditional data warehousing tasks. Hive is designed to maximize scalability, scale out with more machines added dynamically to the Hadoop cluster, performance, extensibility, fault tolerance, and loose coupling with its input formats. RDBMS stands for Relational Database Management System. RDBMS is the basis for SQL and for all modern database systems like MS SQL Server, IBM DB2, Oracle, MySQL, and Microsoft Access. A relational database management system is a database management system that is based on the relational model as introduced by E.F. Code. Below are the key features of Hive that differs from RDBMS. First is query language. HiveQL supports more kinds of data types than SQL, including primitive and complex types. It is very easy to develop and use. Hive resembles a traditional database by supporting SQL interface, but it is not a full database. Hive can be better called as data warehouse instead of database. Hive enforces schema on read time, whereas RDBMS enforces schema on write time. In RDBMS, a table's schema is enforced at data load time. If the data being loaded doesn't conform to the schema, then it is rejected. This design is called schema on write. But Hive doesn't verify the data when it is loaded, but rather when it is retrieved. This is called schema on read. Schema on read makes for a very fast initial load, since the data does not have to be read, parsed, and serialized to disks in the database internal format. The load operation is just a file copy or move. Schema on write makes query time performance faster, since the database can index columns and perform compression on the data, but it takes longer to load data into the database. Hive is based on the notion of write once, read many times, but RDBMS is designed for read and write many times. In RDBMS, record level updates, insertions and deletes, transactions and indexes are possible, whereas these are not allowed in Hive because Hive was built to operate over HDFS data using MapReduce, where full table scans are the norm and a table update is achieved by transforming the data into a new table. In RDBMS, maximum data size allowed will be in tens of terabytes, but whereas Hive can hundreds of petabytes very easily. RDBMS is best suited for dynamic data analysis and where fast responses are expected, but Hive is suited for data warehouse applications, where relatively static data is analyzed. Fast response times are not required, and when the data is not changing rapidly. Hive is very easily scalable at low cost, but RDBMS is not, so it is very costly to scale up. While the tables are logical data units in Hive, table metadata associates the data in a table to HDFS directories. The primary data units and their mappings in the HDFS namespace are as follows. Databases. Namespaces function to avoid naming conflicts for tables, views, partitions, columns, and so on. Databases can also be used to enforce security for a user or group of users. Tables. Homogeneous units of data which have the same schema. When you store data in Hive, you first need to create databases and tables on Hive, which generates named directories under the Hive directory on HDFS. Later, when you store Hive's files, metadata can match file data according to these directory names. Partitions. Each table can have one or more partition keys to determine how to store data. Partitioning, in addition to being a storage unit, allows users to effectively identify rows that meet specified criteria. For example, we partition student information tables based on gender. Therefore, if only male data are analyzed, the query can only be run on the relevant partitions of the table, thus greatly accelerating the speed of analysis. Specific partitioning requirements depend on data type and user requirements. It is the user's job to guarantee the relationship between partition name and data content. Partition columns are virtual columns. They are not part of the data itself, but are derived on load. Bucket. Data in each partition may in turn be divided into buckets based on the value of a hash function of some column of the table. Bucketed tables are fantastic in that they allow much more efficient sampling than do non-bucketed tables, and they may later allow for time-saving operations such as map side joins. Note that it is not necessary for tables to be partitioned or bucketed, but these abstractions allow the system to prune large quantities of data during query processing, resulting in faster query execution. As we know, The database is among the most important and powerful parts of any organization. In the meta store, the database keeps all the information related to our database, tables, and relations as metadata. Whenever you want to know something about your database, then you can find it easily in the meta store. The meta store acts as a system catalog for Hive. It stores all the information about the tables, their partitions, the schemas, the columns and their types, the table locations, etc. Metadata determines the association relationships, while the operations in Hive changed the data. They also updated the new mapping information to metadata. So we must not use hdfs command to modify the data in Hive directory, which will cause the corresponding data loss of mapping information. All Hive implementations need a metastore service, where it stores metadata. It is implemented using tables in a relational database. By default, Hive uses a built-in Derby SQL server. Apache Derby is a full-featured RDBM with a small footprint, either embedded into a Java application or used as a database server. It provides single-process storage, so when we use Derby, we cannot run instances of Hive CLI. Whenever we want to run Hive on a personal machine or for some developer task, then it is good. But when we want to use it in a cluster, then MySQL or any other similar relational database is required. MySQL is a good general choice used widely. It can be configured for high availability and reliability through mirroring and master-slave. It's well understood by a lot of programmers and integrates well into a lot of platform software. MySQL not only provides a solid and comprehensive metadata storage function, but also allows you to view existing metadata information clearly through the MySQL client. Hive users have a choice of 3 runtime frameworks when executing SQL queries. Users can choose between Apache Hadoop, MapReduce, Apache TEZ, or Apache Spark frameworks as their execution backends. MapReduce is a mature framework that is proven at large scales. However, MapReduce is a purely batch framework, and queries using it may experience higher latencies, tons of seconds, even over small data sets. Apache TEZ is designed for interactive query and has substantially reduced overhead versus MapReduce. The Apache TEZ project is aimed at building an application framework which allows for a complex, directed acyclic graph of tasks for processing data. It is currently built atop Yarn by allowing projects like Apache Hive and Apache Pig to run a complex DAG of tasks. TEZ can be used to process data that earlier took multiple MR jobs. Now is a single TEZ job as shown below. Apache Spark is a cluster computing framework that's built outside of MapReduce, but on top of HDFS, with the notion of composable and transformable distributed collection of items called Resilient Distributed Dataset, RDD, which allows processing and analysis without the traditional intermediate stages that MapReduce introduces. Users are free to switch back and forth between these frameworks at any time. In each case, Hive is best suited for use cases where the amount of data processed is large enough to require a distributed system. In this section, let's talk about Hive's commands. There are many ways to use Hive. You can run SQL or SQL files directly on the Hive startup parameters, or you can use the Hive command line interface from the shell. Hive provides remote connections. Hive Server 2 is a server interface that enables remote clients to execute queries against Hive and retrieve the results. Hive also supports JDBC for programmers to develop applications. Hive's commands are very flexible, and you can use them on the shell line. Commands are non-SQL statements, such as setting a property or adding a resource. They can be used in HiveQL scripts or directly in the CLI or B line. From the Hive shell, you can use quit or exit to leave the interactive shell. Executes a Hive query and prints results to standard output. Executes a DFS command from the Hive shell. Sets the value of a particular configuration variable. Note, if you misspell the variable name, the CLI will not show an error. The basic commands for operating the database are listed here. It's worth noting that you have to use commands to select an existing database before you can manipulate a table. The basic commands for operating the table are listed here. Here we will mainly explain the order of table creating. Create table creates a table with a given name. An error is thrown if a table or view with the same name already exists. You can use if not exists to skip the error. A table created without the external clause is called a managed table because Hive manages its data. If Hive creates an external table, you need to specify a directory for HDFS to store data files. When deleting external tables in Hive, only metadata is deleted, not data in HDFS directory. So external tables are more reliable and secure. Partitioned tables can be created using the partitioned by clause. A table can have one or more partition columns, and a separate data directory is created for each distinct value combination in the partition columns. Further, tables or partitions can be bucketed using clustered by columns, and data can be sorted within that bucket via sort by columns. This can improve performance on certain kinds of queries. Row format is used to specify separators. Use the delimited clause to read delimited files. Enable escaping for the delimiter characters by using the escaped by clause. Escaping is needed if you want to work with data that can contain these delimiter characters. Hive supports multiple file formats. Users can choose different file storage formats according to different needs, such as sequence file, text file, RC file. Different file formats have different effects on reading and writing. Stored as plain text files. Text file is the default file format, unless the configuration parameter Hive.default file format has a different setting. You can use the following commands to manipulate data on a table. Next, I'll show you how to use Hive in E-MR. Click New Job. Input job name and description. Choose job type. Click OK. Paste the Hive scripts here. Scripts include creating databases, creating tables, and loading commands. This time, we choose a file on OSS. Select Object Storage Service to go to the OSS console. Click Upload to upload the student file. Click Insert an OSS URI. Click Design Workflow. Design a workflow with start and end nodes. Choose the Hive job we designed. Click OK. Click Run. View job logs and confirm the results. Click Query here. We use commands to query table data. In the following information, we see table data. Today, we mainly learned how to use E-MapReduce and how to use Hadoop and Hive in EMR. Let's review some of the contents of this lesson. What is EMR? EMR is a big data processing solution that runs on the Alibaba Cloud platform. EMR is built on Alibaba Cloud ECS instances and is based on open source Apache Hadoop and Apache Spark. EMR allows you to use the Hadoop and Spark ecosystem components such as Apache Hive, Apache Kafka, Flink, Druid, and TensorFlow to analyze and process data. You can use EMR to process data stored on different Alibaba Cloud data storage servers, such as OSS, SLS, and RDS. What is Hive? Hive is a data warehousing infrastructure based on Apache Hadoop. Hive's components include driver, query compiler, metastore, execution engine, and client. And it is important to note that you cannot use HDFS directly to manipulate data in the Hive directory over Hive. Otherwise, metadata will fail. Features of Hive include tools to enable easy access to data via SQL, a mechanism to impose structure on a variety of data formats, access to files stored either directly in Apache HDFS or in other data storage systems such as Apache HBase, query execution via Apache DZ, Apache Spark, or MapReduce.